OK. One more attack we have to talk about with DNS is something called the Kaminsky attack. So if we think back to the off-path attacker, we said that the ID field is random, and the ID field is 16 bits long. So an off-path attacker has 1 in 65,000 probability of guessing that field right and poisoning the cache. Another way to put that is that the attacker has to try roughly 65,000 times in order for their off-path spoofing attack to succeed. Is 65,000 a lot? It doesn't seem like one of those astronomically big numbers that we've talked about in the past. Like 2 to the 128 was enormous. 2 to the 256 was like atoms in the universe large. 65,000 by comparison is kind of small. So one question you might have is whether that's enough. Is an attacker who tries 65,000 times something that's plausible that we have to worry about? Or is it something that is out of anyone's reasonable threat model? So for the longest time on the internet, for a bunch of decades, people thought 65,000 was good enough. Attackers cannot try 65,000 times. But sometime in the 2000s, one person disagreed with that. And who disagreed? Dan Kaminsky disagreed. And he found an attack that made 65,000 a plausible number for attackers. And this attack is named for him. So this is what we're going to look at. So first, let's think about why 65,000 was long thought to be reasonable. And then we'll see what Dan Kaminsky found that made 65,000 a lot more plausible for attackers. So I guess I don't have slides for this. I'll say it out loud. Think about what happens if an attacker loses the race condition. So here we have a slide where the recursive resolver makes a request. And the name server wants to send a legitimate response. And the attacker's response wants to get there first. Also, if this is an off-path attacker, their race condition has to win. So they have to get their answer there first. And they have to guess the ID field correctly. So let's think about what happens if the attacker wins and what happens if the attacker loses. If the attacker wins, the race condition is 1, and they guess the correct ID with probability 1 in 65,000, then the attacker has won. Their poison record lives in the cache, and it's going to live there for as long as that TTL says. So it might live there for days or weeks, and anytime the recursive resolver is looking up that record, they're going to pull out that malicious record. So it's a total victory for the attacker. What happens if the attacker loses? What if the attacker loses the race condition or they guess the wrong ID, so their answer is not accepted? Well, in that case, because the attacker has lost, the name server is going to send a legitimate response back to the resolver, and the resolver is going to cache it for a day or a week. And if that answer is cached, then this recursive resolver is not going to make another request for the same domain to IP mapping. If someone asks this recursive resolver anytime in the next week for the IP address of eeks.berkeley.edu, they're not going to make a request. They're just going to go in their cache, pull out the answer, and that's it. So the attacker doesn't get another chance to do another spoofing attack. That's the key idea that people thought was defending DNS against off-path attackers. If you lose, the legitimate answer shows up and gets cached for, let's say, a week. And that means that this attacker is locked out of trying for a whole week. For this entire upcoming week, the recursive resolver is not going to try again. So this attacker is not going to get another chance to race and guess the ID until next week. So this attacker is stuck waiting for an entire week before they can try again. So when we said 65,000 and we were thinking about whether that number was large enough, this model makes it seem like 65,000 is safe. The attacker only gets to try once every week to poison a specific domain. If they lose, they have to wait another week for the cache entry to expire. So for them to succeed, they'd have to try 65,000 weeks. That's an enormous amount of time. So that was the argument for why off-path attackers would not succeed in DNS spoofing attacks with very high probability. It's because of that 1 week of caching. That was the argument for the longest time. So what did Dan Kaminsky find that broke this entire argument and sent the entire internet into a panic? This is what he came up with. What if, instead of making a request for the real www.google.com, what if we tricked the resolver into making requests for fake, non-existent domains? So here are some example fake domains that the recursive resolver might ask for. What if, instead of asking for the IP address of www.google.com, we somehow made the recursive resolver ask for the IP of fake1.google.com, which doesn't exist, and fake2.google.com, which also doesn't exist, and fake3.google.com, which also doesn't exist. Now the recursive resolver is making requests for these fake domains. So going back to that picture, think about the win and lose conditions once again. If the attacker wins, then the recursive resolver makes a request for a fake domain. The attacker replies with a malicious response, and in the additional section, we can throw in a real domain. So for example, in the answer section, we can leave it blank, or we can put something dummy. It doesn't matter because this is a fake domain and it's not our goal. But in the additional section, we can say, by the way, in case you're curious, here's the IP address of www.google.com, and here's a malicious IP address to go with it. So the resolver is making a request for this fake domain, but in the attacker spoof response, we throw in this additional malicious record that has the real domain that we're trying to poison. So if the attacker wins, they can successfully poison www.google.com. The recursive resolver was requesting a fake domain, but the attacker can use that additional section to inject a malicious record for the real domain that they're trying to poison. So in other words, if the attacker wins, it's still total victory. They've gotten a malicious record into the cache, and it's going to live there for the next week. So the attacker's win condition is the same. That means this attack is possible. Now what if the attacker loses? What if the race fails or they guess the wrong ID? In that case, the berkeley.edu name server would send its answer there. And what would the berkeley.edu name server's answer say? It would say something like, you asked for fake1.google.com, and that doesn't exist. So what would the recursive resolver cache? It might cache nothing. It might cache that the fake domain doesn't exist. But it's not going to cache anything about google.com. That's the key idea. Because we're asking for fake domains, even if the attacker loses the race, nothing useful gets cached. All that you get in your cache is that this fake domain doesn't exist, or maybe the resolver doesn't even cache that. Either way, www.google.com is still uncached, so the attacker can try again right away by asking for another fake domain. So in other words, this idea is going to allow the attacker to try as many times as they want by having the resolver request all of these fake domains. So this is the difference between trying once a week and trying as many times as you want, as fast as the network allows. That's a really big difference. Imagine trying something and you fail, and you have to wait a whole week before trying again, or trying something and it fails, and you can immediately try again by asking for one of these other fake domains. That's the Kaminsky attack, and that's what turned 65,000 from a very unrealistic number to something that's very plausible for attackers. So that's the high-level idea. I'll show you some pictures coming up next.